Hooke's law describes the behavior of a spring. We have seen that in the lab. It also models the natural elasticity of solid materials. Hooke's law is valid for small deformations when the spring is stretched a small amount relative to its overall length. Hooke's law describes a linear restoring force provided by the spring. This is a tension within the material. When the spring is relaxed, that means there's no force pulling on the spring and there's no spring force responding to it. Therefore, the spring is in its equilibrium state or at its natural length. If you stretch the spring pulls back towards its natural length. If you compress the spring and press it inwards, the spring force pushes back outwards, again trying to restore itself to its original length. A spring has a constant, lowercase k. The spring constant measures the stiffness of the spring or the strength of the spring. A spring with a very low spring constant would be like a slinky that easily changes length. A large spring constant would be the springs you might see in the shock absorbers on the wheels of rail cars, for example. When we derive the equation for Hooke's law, we assume that one side of the spring is fixed in place, that it's anchored to a wall or to some other fixed point, and then we place the origin, x equals 0, at the other end of the spring. When the spring is at its natural length, that is our x equals 0. And we're assuming that the spring is aligned with the x-axis. In this situation, the equation for the spring force is F equals negative kx. Here, k is the spring constant. That's a measure of how strong the spring is. X is the position of the end of the spring. Notice that if the position is positive, then a positive times a negative gives us a negative force, a force pointing to the left. If the position is negative, that means that the spring has been compressed, and a negative times a negative gives us a positive value of the force. The force pushes back to the right. So this negative sign here indicates the restoring force, the fact that the spring is pushing back towards its equilibrium point. It is acceptable as well to omit the negative sign here. That would give you the magnitude of the spring force, and you would simply have to be aware of that and include the direction independently. You can notice here as well that this equation is in the format y equals mx. So if we plot the elongation of the spring versus the spring force, we would expect to have a linear relationship, and the slope of that straight line would be the spring constant. Force is measured in newtons, elongation is measured in meters, and so our spring constant is measured in newtons per meter.